Something is wrong? Huh? Oh, that will be corrected. So in the last class, we talked about DFS in graphs. That is how to do a traversal on a graph using depth first strategy. And if you remember, in that strategy we use two integers d and f. That is, the first time you visit a vertex, you record it in the d field, and when you last visit the vertex, when you finish visiting that vertex, you record that time into the f field of the vertex. Now using these two integers, we have also classified the edges of the graph. So we basically said there are four types of edges. One is tree edge. What is a tree edge? Ij is a tree edge if Vj dot, you have to remember what we did for representing the graph. What is the data structure? Vj dot pi is the field which will have the pointer to the vertex from which the vertex j is being visited. So Vj dot pi, if this is equal to I, then Ij is a tree edge. Basically, tree edges are the edges through which you are performing the DFS. Then there is a back edge, and back edge is Ij again, so that j is an ancestor of I in the tree which you have developed through DFS. So if you draw only the tree edges, it gives you a tree. Actually, if there are more than one component, it will give you a spanning forest. So in that spanning forest, we can talk about children, we can talk about descendants, which are also ancestors. So I am referring here. So back edge is Ij is in back edge if j is an ancestor of I. So you are going up the tree, it means. And similarly, what is a forward edge? Is just opposite of back edge. Ij such that j is a descendant of I. And we also have some other edges which are called the cross edge. Cross edges are those edges which are the rest. So basically those which are not tree edges, not back edges, not forward edges, they are called the cross edges, rest of the edges.
So forward edge include the tree edge?
In a sense, yes. Right. Because, yes, it will, by this definition, forward edge also include. But you can say those are the forward edges which are not tree edges. You can always partition that state. Right. So here you can say forward edge Ij such that j is a descendant of I and such that Ij is not a tree edge. You can put an and condition. So these are the classification of the edges of the graph through DFS. And here is a very nice nesting property of this D and F field. So this is called the nesting property. All this we are referring to the previous class. So vertex, here is a nesting property. Vertex J is a proper descendant of vertex I in DFS forest. DFS forest means the forest we have computed through depth first search. of the graph G of VE if and only if this is true, Vi dot D is less than Vj dot D less than Vj dot F less than Vi dot F. So what is the picture? Vertex J is a descendant. So here is I and somewhere, so there is a path basically. So this is I, this is J. In the tree, something like this will happen. When it will happen, you can see it must be the case that I is visited before J, right? So that's why VID is less than VIF. Sorry, VID is less than VJD. Because I is being first visited earlier than J. That's why this inequality. Now both D must be less than equal to F, not equal to, less than F by definition. So these two must be less than this. Now if you see the way we are marking the finish time, it must be the case the one which is visited earlier will be marked later. So that's why VIF is greater than VJF. And if this is called the nesting property. If this is satisfied, then you can also say that J must be descendant of I. So given a DFS forest and I give you two nodes J and I and ask whether which one is descendant of which one. So you can just check the D and F field and verify this, then immediately you can say whether J is a descendant of I. Because if this is not valid, if this, then J cannot be a descendant of I, because this is an if and only if condition. Alright. Now here is the next property for DFS. If the, so far we have said the graph we have taken is a directed graph, and in the directed graph we have forward edge, we have backward edge, and also the cross edges. But if the graph is not directed, you can verify there cannot be any cross edge. It's only during, if it is directed graph, cross edges are possible. So in a undirected graph, there are only tree edges, backward edges, and forward edges. If you remember, in the cross edge will happen, suppose I have a tree something like this, and there is something else is there, and there is a cross edge like this. There is one part here, there is another part here, and there is an edge here. But see, this can happen since there is a direction. I could not visit, when I visited this node, I could not visit this node through this edge because there is a direction associated with it. But if there is no direction, if it is an undirected graph, when you visit this node, automatically you will visit this node. They will be in the same component. So this will not appear as a cross edge. So that is the next thing. So if the graph VE is undirected, then there are no cross edges. So let us see. I just want to take an example and show you why it cannot have. Okay. So let's take the similar example what we had previously. So this time there is no direction, only edges. So suppose we start from say this one, from this node. So it's starting, we go this way, 1, so this becomes 2, then from here we go this way, this becomes 3, then we visit this becomes 4, then we visit this 5, then we visit this 6. See, in directed version of the same graph, if I remember correctly, we could not visit this part because all the directions were this way. But now we will be visiting this. So there will be no cross. This edge probably appeared previously in a cross manner. So this will be visited. So this becomes 7. Then this visited. This becomes 8. Now this is finished. 9, 10, 11, 12, 13, 14, 15 and 16. So this will be the D and F field if you visit the same graph which is undirected. And if I draw the tree now, it looks like something like a chain. So this is 1 over 16, 2 over 15, so this is the edge we visited. This is 3 over 14, 4 over 13, 5 over 12, this is 6 over 11, actually some more are there. Okay, I don't have space to draw, I mean like 6 and then 7 over 10, 8 over 9 will come. And if you draw the other edges, you can see all the others are back edges in this case. So like we have from 5 to 12 to 1 to 16 there, so this will be a back edge. Actually, since we don't have any direction on the edge, you cannot say this is a forward edge or back edge. So there are only two types of edges now. Either they are tree edges or non-tree edges. Because I cannot give the direction like this. There is no direction now. 5 to 12 to 1 to 16. Similarly 4 to 13 there is an edge to 2 to 15. Then 3 to 14 there is none. 4 to 13 there is 2 to 15. Then 5 to 12 there is one more edge to 2 to 15. Then 6 to 11 to 1 to 16 there is an edge. So there are some more edges. Okay. So you can see this graph has tree edges and non-tree edges. There are no cross edges and we cannot talk about forward and backward edges because there is no direction on the edge anymore. So this will be the situation if you run your DFS on undirected graphs. Now, I already told you DFS is a very basic algorithm. It's like giving you some basic information about the graph when you traverse the graph in this manner. What are the basic information you can get from this DFS? One information is DFS can be used to find the connected component of an undirected graph. What is a connected component? I am going to give you the definition for it. First, vertex V is connected to vertex U if U is equal to V or a neighbor of V is connected to U. So this is a recursive definition. So vertex V and U are connected, either V is equal to U or a neighbor of V is connected to U. So basically it means, this definition is meaning that in the graph between the vertices V and U there is a path. Then you call V and U connected in the graph. So you can go from V to U using the edges of the graph. Then only you call that V and U are connected. And what is a connected component? So a connected component of VE is a maximal subset of U, which is a subset of V, is a maximum subset of vertices, so that all vertices in U are pairwise connected. So this is a very precise definition of what is a connected component. So first we define what do we mean by two vertices connected. That is this definition. Now after that we are saying a connected component in a graph is a maximal subset. So you take a subset of the vertices and you take the maximal as long as you can, so that in that subset any two vertices are connected. So let me just draw a picture and it will be immediate to you what is a component. And that's the way you always call intuitively probably. So suppose I have this graph. Suppose this is the graph. So this is a VE graph. How many connected components does this graph have? 3. Because this is a maximal subset of vertices such that any two vertices are pairwise connected. You cannot include any more vertex from the rest of the graph so that this component remains connected. This is one component, this is another component, and this is the third component. So there are 3 components now. So there are 3 components. Sometimes we drop the connectedness. So we say instead of connected component, we say 3 components. So 3 components. Now given a graph, how many components are there in the graph? It's a very basic structural property. How many components are there in the graph? So how can you determine how many components are there in the graph? We can run our DFS algorithm on the graph, and if you remember in the DFS algorithm, first the uppermost routine, it goes over all the vertices in the array. Whenever it is going over the vertices of the array, it's checking whether that vertex is visited or not. If it is not visited, it gives a fresh visit call. So the number of times you give this fresh visit call is actually equal to the number of components. It should be very obvious to you. If you see, like in this picture, I just suppose I have taken this vertex and given a visit call. This visit call will visit all the vertices, but it cannot visit these vertices because they are not reachable from the vertices. So once you have given a visit call, fresh visit call here, that has finished all these vertices, then in that uppermost routine, that while loop or whatever, the for loop, will go over all these vertices probably, and when it will come here, one of these vertices, it will see this has not been visited, and it will give a fresh visit call again. So once it gives this fresh visit call, you know that you have encountered a new component. Again, this component will visit these 2 vertices and it will not visit the third vertex here. So for this third vertex, again you have to give a fresh visit call. So 3 fresh visit call will tell you there are 3 components. So this is one of the very simplest and probably most efficient way to detect the number of components in a graph. Now there is another application of DFS. Yes, please.
If the graph is directed,
I have not talked about what happens if the graph is directed, because then I have to define what do we mean by connectedness in a directed graph. So let's, for the time being, let's not assume the directed graph. But again, even in directed graph you can do this. Okay, but it will be a little bit more complicated. Now there is another property which you can detect using the DFS. That property is whether the graph has a cycle or not. So DFS finds cycles in a graph. So given a graph, whether the graph has a cycle or not can be detected again using DFS. This is also a very important structural property. If a graph is connected and does not have a cycle, then what is it actually? It must be a tree. A graph which is connected and does not have a cycle is a tree. That's the definition of a tree actually. How do you define a tree? A tree is a graph which is connected and does not have a cycle. So suppose I take out the connectedness. I just say a graph which does not have a cycle. What is it then? It's a forest. That's the definition of forest. Forest is a graph which is acyclic, which does not have any cycle. So given a graph, one would like to know whether it is a tree or a forest or a graph in a general sense, whether it has a cycle. So how do you detect again? Again we can run the DFS and check if there are any back edge or any non-tree edge. Basically we said there is no back and forward in undirected graph. So in undirected graph we will see whether there is any back edge, non-tree edge. And for a directed graph, how can you detect whether there is a cycle or not? Yes, there you check whether there is a back edge in the graph or not, and whether something has a back edge or not, again you can check with D and F fill. So that is why we use this D and F fill. While doing the DFS you can do something more, and from that one you can get some other structural properties. So here it means every back edge in a directed graph forms a cycle, and this becomes non-tree edge if it is undirected graph. Suppose a graph is connected and I tell you there are n vertices in the graph, okay, and there are say m edges in the graph. Can you tell me how many non-tree edge can be there? If the graph is connected and suppose it has n vertices and m edges, how many non-tree edges can it have? M minus n plus 1, right? Because a tree can have how many edges? An n vertex tree? N minus 1 edges. So the rest of the edges must be non-tree edges. So that means m minus n plus 1 is the number of non-tree edges if the graph is connected. And if you know beforehand how many components are there, even you can put that component value and tell how many non-tree edges are there. So now suppose I give you a problem. I ask, suppose a graph has n vertices and m edges. I give you the value n and m. And suppose a graph is connected. Determine whether the graph has a cycle or not. How do you solve this problem? Positive or not. So it's a constant time algorithm. You don't have to do all these DFS at all. Just check the value of n, check the value of m, and check whether m minus n plus 1 is positive. If you know the graph is connected, immediately you can tell whether the graph is cyclic or not for undirected graph. But suppose somebody is not happy to know only that there is a cycle or not. Suppose he wants to find out one cycle, then you have to run the DFS and present the cycles. So these are the two applications of depth first traversal. Now I will show you another application of depth first traversal which can solve another important problem on directed graphs. So that is called topological sort. Directed graph also sometimes called the digraph. So a cycle in a directed graph is a sequence of vertices V0, V1 up to say Vm, where Vi belongs to V, so that Vi plus 1, there is an edge, it belongs to E, and since it is a cycle, Vm, V0 also belongs to E. So that is the definition of a cycle. So it is a sequence of vertices such that between every consecutive vertices there is an edge, and from the last vertex to the first vertex also there is an edge. A digraph VE is called directed acyclic graph, or in short it has a name, it's called DAG, D-A-G, DAG. Sometimes people call it as a DAG, directed acyclic graph. This is a standard name if it has no cycle. Now this topological sort, I have not defined yet, can be done only on DAGs. If there is a cycle, we cannot do a topological sorting of the graph. Now let me tell you what do we mean by a topological sort. So topological sort for a DAG is an ordering. It's an ordering of vertices V1, V2 up to say Vn, so that I less than j if Vi, Vj is an edge. So what does it mean? It means you give an ordering on the vertices, you just enumerate them in some order. But if that order has this property, suppose Vi, Vj forms an edge, then this vertex must appear before this vertex in the order. That's the only condition. So let me take one graph. Sorry, this will not have. Yes, this is fine. So suppose I have V0, V1, V2. You can see V0, V1, V2 is a topological sort. V0, V1, V2, yes. Why? If I ordered these three vertices in this manner, V0, V1 and V2, you cannot have any two vertices which has an edge and the destination appears earlier than the source. It is not happening here. So let us see. V0, V1 is an edge, then V0 must appear before V1. That has happened. V0, V2 there is an edge. V0 must appear before V2. Yes, it has happened. V1, V2 is an edge and V1 must appear before V2. That has happened. Suppose I take V1, V0, V2. This is not a topological sort anymore because it violates say V1, V0. V1, V0 is an edge, but V1 has appeared before V0. So this is called a topological sort. Why this problem is important? This problem is important where in applications you would require to solve something satisfying all dependencies. So suppose there are several jobs or several things which are happening depending on something else. So you can express this scenario using a directed graph. So you can say job 1, so say this is J1, J2, say J3, J4. Suppose there are 4 jobs. And suppose J2 can happen only when J1 is finished. When J1 is done, then only I can start J2. So you can put that information like this. And suppose J4 can happen only when J3 is finished. So again you can put this way. And also J4 I can put some more constant that J4 can take place only when J3 is done and J2 is done. And again I can say J3 will be done only when J2 is done and probably J1 is done. Suppose I have this scenario. You can see that it may be very complicated also. So in this case one would like to say, see, give me at least one sequence in which I can schedule all the jobs, at least which is feasible. That scheduling can be done. So that when something I require to do in that sequence, all the ones which are required to be done before that has been done. So what does that mean? To solve this problem, basically you are trying to do a topological sort on this directed graph. And you can see the directed graph, this topological sorting can happen only if the directed graph is acyclic. Otherwise you cannot do. Suppose we have a graph like this, say with 3 vertices, with this dependency. So suppose J1, J2, J3. No way you can schedule all the jobs such that all the requirements will be valid. Because J1 is dependent on J3, J3 is dependent on J2, J2 is dependent on J1. It's a cyclic dependency. So you cannot solve this problem. So that means topological sorting, that's why actually we are asking for topological sorting on directed acyclic graph. You cannot do a topological sorting on cyclic graphs. There is no such ordering at all possible. Okay, and that is the motivation why topological sorting is sought for directed acyclic graph, to find out these dependencies. At least give me one scheduling of the vertices or one sequence of the vertices which does not violate these constraints. So again, this problem of topological sorting can be nicely solved using depth first search. First of all, as I already told you, here is the first claim which I have already claimed. So let me put it, V, how would you verify whether the graph is acyclic? V is acyclic if and only if DFS is no backage. So first you run a DFS on the graph and check whether there is a backage or not. If there is no backage, then only we proceed for the topological sort on that graph. If there is a backage, you stop and just output that it is not possible to do a topological sort. Now here is the second claim, and when I put the second claim, algorithm is almost immediate. Second claim is if UV is an edge, then what happens? What do you expect? If V is an edge, UV is an edge, then VU dot F is less than VV dot F. If UV is an edge, then its F field must be higher than its F field, right? If UV is an edge, then this must be true. F field must be higher, then we will give a proof. Don't worry. So what we can, so once this is true, algorithm is automatic. You first run the DFS and output the vertex whenever it is finished. Output a vertex whenever it is finished. What does it mean? From this claim, it means you are outputting the vertices in the reverse order of the topological sort, because you are outputting the vertex whenever it is finished. So the ones which are outputted last, they have the highest F field, and according to this, there cannot be any edge in the reverse direction of this sequence. So we are outputting in the reverse direction of topological sort. So suppose I have outputted, say, U here and say, sorry, V here and U here in the sequence. So I know the F field of U is higher than F field of V. So it can only allow that there is an edge from U to V, not V to U. That's not possible. So if I have outputted this way, there is an edge from U to V only. There can be. So it means the topological sort ordering is in this direction. It gives you one ordering which is consistent with the condition of the topological sorting. If you go back to the definition of topological sorting, you will see this is consistent. In this direction we are outputting. So first what you can do, you can output in a stack, probably then you reverse it to reverse this sequence, to give you the forward sequence basically. It doesn't matter. So this gives you an algorithm automatically for a topological sort. Remember, for one DAG, there may be more than one sequence of topological sorting. We are just outputting only one. There may be another one. Okay. So now I am going to prove this claim. So how do we prove? So here is the proof. Why this is true. Consider the time UV is explored by DFS. The first time UV, the edge UV is checked. So there are several cases. Case 1, in that suppose when the first time UV is explored, V is an ancestor of U. What does it mean? If V is an ancestor of U and you are checking UV, what does it mean? There is an edge from U to V. It means that this is a back edge, and that is not possible. Already we have taken only DAG. So this is not possible for DAG. Case 2, V is yet unexplored. You have not explored V yet. In that case, it is true. In that case, V becomes a descendant of U. So V U dot F is greater than V dot F. In that case. And here is the case 3. V is already finished. It's already done. In that case, if it is already finished, then definitely U's F field must be greater than or equal to V's F field. Because U is not yet finished, you are exploring it through UV and V is already done. So it must be true, then VU dot F is greater than V V dot F. So all three cases, and these are the all exhaustive cases. There cannot be any other case. In all cases, we have proved that V dot F is greater than or equal to V dot F if UV is an edge. So through F field you can produce a topological sorting of the graph. So how much time does it take? How much time does this take?
Order of V plus E.
Order of, not order of E. You cannot just say order of E because E can be very less and V may be high. I already told you in one of the class. So you have to say this is order of V plus E or order of N plus M. That's the correct statement. Order of V plus E. So this is the linear time algorithm. So in linear time you can do a topological sorting in a directed acyclic graph, which is very useful in many cases.